Okay. Hello all. I'll try not to make this too long. This is the last newest section that we'll cover in this class, and I wanted to go over it because it's not too bad, and I wanted you to take a look at this. And so if you have Calc 3 already, you might be familiar with some of these properties. Okay, so let's get started. So let's say we have two vectors, u and v, and they're given there, and they're just given sort of simplified, but it's represented as, if we represent it sort of in that notation, which we'll get to, then as you all know, that represents an n by 1 matrix, right? And a vector, right? So vector u, vector u is here, and as a matrix is here. Okay, I want to make sure that's clear. So let u and v be any two vectors with n elements. The inner product, and it's also called the dot product, so if you've taken Calc 3, you may have heard it as the dot product, is u transpose with v. And we know that's the case, right? Because u, again, is an n by 1, and v is an n by 1. So we remember, since the interquantities quantities don't match, then we couldn't multiply them together. So, but if we take the transpose, which would be a 1 by n, then we can multiply it, right? So this is what we're doing here, taking the transpose, and so that's the transpose of u, which becomes now a 1 by n matrix, and v is an n by 1 matrix, and so it produces technically a 1 by 1 matrix, right? But it's really just one single quantity, one single number, which let's call it k. Okay, so that's known as the dot product, right? So that's pretty straightforward. And so looking at the next slide, so if we were to find the dot product of u times v given these vectors here, then we take the transpose of u, which would be here, and then multiply it by v, which is here. And it's really just pairwise multiplication, right? You guys know how to do this. So it's 1 times -2, 2 times 0, 3 times 2, and 0 times 0. Okay? And we add those together and we get 8. Then if we take u times w, so this is just practice with the dot product or the inner product. And so this will be u transpose times w. And so again, this is u transpose here. So it's -1 times -2, right? So -1 times -2, and then 2 times 0, and then 3 times -2, and then 0 times 1. And if we add that up, then we'll get 0. I'm sorry, -4. Okay, and C, we do the same thing. So I'm going to leave C to D and D for you all just to practice, right? So just practice and do C and D, okay? Now note that here, so when you check your work, so you can pause the video and check your work, that you get 8 for U times V, or U dot V, I should say the dot product. U dot V is actually equal to v dot u, right? Which is interesting because we don't, the commutative property doesn't necessarily hold, but it does with dot products. Okay, so u times v is actually equal to v times u. All right, and you can see that in an example. Okay, and so now, like I said, so we have some properties for our inner product or the dot product. And so if you have 3 vectors and they're all vectors with n elements, then, like I said, we have what's called symmetry. And it's called symmetry because for the most part, when you're looking at vectors, you look at it in the plane. So if this was more of a sort of visual linear algebra class, we would be doing more shapes and figures to represent that. So we call it symmetry. And if you take any 2 vectors, take their dot products, and then look at sort of the direction on them, plot them on the, say, take 2 vectors that are in R2, and you can play around with that to see the symmetry. It has the additivity product, so property, I'm sorry. So u times v plus w is u dot v plus u dot w, okay? Homogeneity property, which says if you take a scalar c times u dot v, it equals cu dot v, or u to dot cv, okay? So we have that property. And then positive definiteness, yes, okay, don't worry about it. It's positive, right? So u dot u is greater than or equal to 0, and u dot u equals 0 if and only if u is equal to the 0 vector, right? That makes sense. And so why do we have this property? If you think, let's see, u dot u is always it's non-negative. Well, let's think about that. So u dot u is u transpose times u. Well, the transpose of u is just going to give you u1 squared. If you take t, okay, if you take a u, so just try whether you take a u and if you take its transpose, then what's going to happen when you take ut dot u? Well, you're going to have u1 squared plus u2 squared plus dot 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 plus un squared. Okay? Okay. As seen in this example below. So if we have u equal to some vector 1, 2, remember again, that really means 1, 2. This is that as a column vector, right? And so then if you take the transpose, well, that's going to be 1, 2 times 1, 2, and so that's just going to be 1 squared plus 2 squared. Okay. All right. So now so you guys, I think you're good with the inner product, the dot product. Now we're going to talk about something called the norm or the length. Now consider values on a real number line. So whenever we're talking about absolute value, we're talking about distance, although we know it's the absolute value of 3 is 3, the absolute value of -3 is 3, but what that really means is the distance from 0. So for instance, -1 equals 1 because the distance from 0 is 1, right? When we're talking about distance, that's a positive length. So that's why we talk about the notation as absolute value. If we had, let's say, -3 minus a -1, right? That's the same as 3 plus 1, which is equal to 4, and that's 4. So that's really, we put -3 on there. So it's really, we're talking about 3 plus 1. So we're talking about the distance, right? So that's the distance between two values, right? And so the distance between two values on a number line, okay? Wait, I'm sorry, let's go back. Actually, we're talking 3 is positive, not negative, right? So I'm talking about over here. I knew something was wrong with my distance. That didn't look right. All right, so we're talking about 3 here. And so the distance between 3 and -1, right? The distance between that would be 3 minus the -1, which would be 4. So the distance between that would be 4. Okay, so that's what I'm talking about. All right, sorry if I confused you all. Okay, so the length or norm of V is a non-negative scalar, and here's the notation here. Looks like double absolute values, right? Defined by, well, the norm, it's called the norm or the length, is the square root of V dot V. Okay, and we know if it's its own, we know for a single vector, that's just going to be V dot V is just going to be V1 squared, V2 squared, Vn squared, where of course those are the elements, right, in our V. Vn of our column vector. Okay. And so for u and v and some Rn, the distance between u and v can be written here. So the distance of u and v equals the length of u minus v, or, which is the same as the length of v minus u. And in both cases, it's going to be the square root of u minus v dot u minus v. Okay. And so here are some properties of norm. Now this example actually, because I didn't have room on the last page, this is an example to speak to this property here. So we're looking at that in a minute. But so if the length is squared, then it's equal to v dot v, just v dot v, right? Because again, the length is the square root of v dot v. So if we square it, it's just going to be v dot v. And then here we have a scalar. We can pull that scalar out of our vector, and that's a property we have. All right, so just to practice this distance formula here, let u equal the vector 1, 2, and let v equal 5, 7. And so the distance is going to be the length or the norm of 1, 2 minus 5, 7, those coordinates. And so that's going to give us the coordinate -4, -5. which we just square each of those elements, and that gives us the square root of 41. Okay. So I have some for you to try on your own. So just try these on your own, and I might have you guys present these in class tomorrow. So just try, find the following norms and distances given the specific vector. So try this on your own. So u, v minus u, and w minus v. Okay. All right. And the last thing, I think, oh no, I think it's something else. But all these are straightforward sort of computations, so hopefully you guys are okay with this. Normalizing a vector. So to normalize a vector means to find another vector in the same direction as your original vector, but it has a length 1. And so to normalize a vector, we also, our new vector becomes what we call u, and that u represents the unit vector. And so to normalize a vector, so if I give you a vector and I want you to normalize it, then that means you take that vector v and divide it by the length of v. Okay, I erased that because that looks too cluttered. But so that's what that's saying. So another way to say that is you take 1 over your length v and dot it, or it's I'm sorry, this is times because that's just a scalar, times v, right? And so, let's see, given v, normalize v. Okay, well first we need to find the length of v. That's easy. Just take the square root of the squares, take the entries and square them, and then take the square root. Then, so we have the square root of 2 is the length. And then we just take 1 over the square root of 2 and multiply it by our vector. And so we get 1 over square root 2 and 1 over square root 2. And you guys probably remember from maybe pre-calc or algebra that you usually don't like to leave the roots in the denominator, so you want to rationalize your roots, and we get square root of 2 over 2, square root of 2 over 2. And although you don't need to do this, this is a nice check to see if it's a unit vector, because again, the length of it is 1. And so if you take each of those terms and square it, you're going to get 1. Okay. All right, this is the last thing. So definition, u, mv, and rn are orthogonal if u dot v equals 0. Okay. And orthogonal is another way to determine if two vectors are perpendicular to each other. So orthogonal is another word for perpendicular. As you go higher and higher in math, you know we have different phrases for different things. So orthogonal means perpendicular. So determine whether the following vectors are orthogonal. Okay. And if you want, especially for this one, because it's on the xy plane, try plotting those 2 points. So 1, 1 and 1, negative 1. And you will see, or plotting those vectors, I'm sorry, and you will see that they're perpendicular to each other because their dot product is 0. Okay. And u and v here are also orthogonal to each other. Okay, so we are done. This is the end of that. It might be one more thing I want to show you, but it'll be after the exam. And I don't know if I'll get a chance to show you all. It's just something to kind of wrap up everything. But make sure you read the book and go over this, and I'll see you in class tomorrow.